what we were going to discuss in this chapter. We're going to go down to the micro level. We're going to go down to the micro level. We're looking at atomic levels. So we're going to explore a little bit of what the atom is, parts of the atom to refresh your memory so that when you have or start to gain an understanding of how X-rays are formed, you'll understand. So, but before I do that, I want to hear a little bit of recap from chapter 5. So, Naomi, tell me where X-rays are made. Exactly where X-rays are made.
Exactly where they're made. It's after that actual focal spot, at that effective focal spot. Is that right?
Right. Well, that's where they are aligned. And the effective focal spot is the path. It's just like, let's just say you're going to take a path through the forest, right? Mm-hmm. So the effective focal spot is the path to directing those X-rays. But you said it. The X-rays are formed at the actual focal spot. Perfect. That is exactly where X-rays will be made. Perfect. Great. So let's talk about a refresher. What does the filament, John, liberate?
Electrons.
Electrons. So, thank you, John. Luke, what kind of charge does the electrons have that originated from the filament?
Negative.
They have a negative charge. Do they also have mass?
No.
If they contain mass and they have weight. So because they are a particle, they do have weight or mass. Mass that's measured in weight. Good, perfect. Let's see. What kind of electrons, the filament electrons, Jonan, what was their original atomic number? Where did those electrons originate from in the filament? They were boiled off from what specifically?
Tungsten.
The tungsten atoms that made up the filament, correct?
Mm-hmm.
Beautiful. Perfect. The flowing of those liberated electrons. How did we get those electrons to flow?
By increasing the positivity of the cathode side.
Cathode or anode? Anode side. So good. We increased the attractiveness of the anode side by applying electricity. Correct? Good. To the anode side. Sharon, the flowing of these electrons, what kind of energy do these electrons now possess? They were stationary and now they are flowing.
Is it negative?
Energy. We're talking about energy, a type of energy.
Oh, there's no charge.
Okay, good. I see where you're going with that. I see where you're going. So the flow, thank you, Sharon. The flow, Stephanie. Remember, the electrons were sitting in the space cloud, right? The space charge. They're stationary. And Jaleisha just said we attracted the anode and we started the flow. What kind of energy do these electrons now possess? With the K.
Kinetic energy, but it goes through the tube current.
Kinetic energy, correct. However, all of the electrons flowing over creates tube current. But the question is, what kind of energy do they possess? And that is kinetic energy. Make sense? So the electrons were stationary. We had to draw them over. Correct? So now they possess kinetic energy. Now, we're going to spend some time talking about the kinetic energy and the actual focal spot. Make sense? Anybody confused on where I'm at right now? Nope. All right, we'll settle on up because we're about to take a ride. Okay. Can everyone see my slide? Yep. So, when we're thinking about photons, the word photons means what, Amy?
X-ray.
X-ray. So when we're thinking about creating photons or creating X-rays, we know that this is the X-ray tube, and this tube has all the components that we need in order to create X-ray, with the application of a stator on the outside, right, so that we can rotate that anode disk, and we need electricity. So we know that electricity has traveled to the anode, cathode, and filament. We know why electricity has traveled to these parts, correct? Everyone know why electricity has traveled to anode? What do we need electricity for on the anode side? Do I have to volunteer?
Which portion? Why do we need
The
electricity?
anode. Why do
On the
we
anode
put
side?
electricity to the anode side?
To turn the rotor?
To turn the rotor, right? That's going to be the stator. The electricity is applied to the stator to turn the rotor. Perfect. Perfect, perfect, perfect. But what also, in the form of voltage, is applied? Why is voltage applied to the anode? Again, Shannon.
To create the potential difference.
To create the potential difference. So we can start igniting the flow. We can start initiating the flow. Why is electricity to the filament, son? Why is there electricity applied to the filament? What do we want the filament to do in the cathode?
The filament boil up the.
We want it to heat up so we can have thermionic emission and liberate those electrons, correct?
Yeah.
And then we want the focusing cup to focus those electrons into a nice little path so they become tube current. Perfect? Everyone understand that? So this is why we're incorporating electricity. Okay, perfect. So now that we're there, electrons have been boiled off the filament and the streaming across to the anode. We know that. That is called tube current. So let's talk about what the interaction happens. We talked about what was the actual focal spot. We also talked about the effective focal spot. We talked about the anode heel effect. But right now, we are going to discuss what is occurring, what is happening at the actual focal spot. Okay? Everyone here with me? So, the filament electrons, which is the electrons that have been boiled off, that come from the filament, the tungsten in the filament, the electrons boil off, they're flowing over. Now they interact with the focal spot, they penetrate the face, which is here, the face of the anode, or the face of the stationary anode, of the target to a depth of about 0.5 millimeters. So most of the tungsten with rhenium, not all of it, is interacted with, only to a depth about 0.5 millimeters. So the filament electrons are interacting with now the atoms, the tungsten atoms inside of the target. So the filament electrons are now interacting with the tungsten target atoms. Everyone understand that? So the filament electrons are going to come over and they're going to have some type of interaction at the actual focal spot or the atoms that occupy that actual focal spot. And what are those atoms made up again? Tungsten. Questions? Pretty simple, right? Now we're talking about the actual target space. So we can say, we know this. We know what's happening here. We've already discussed it. We know there's a tungsten target. We know that there's filament electrons. We know that there's the tube current, which is the flowing of those electrons are going to collide with the target atoms, right? The target tungsten atoms. And so there are going to be some interactions. 2, not 3, possibly 3 different interactions, okay? So the first thing that I want to discuss is, what does a tungsten atom look like? What does a tungsten atom look like? So when we have a tungsten atom, this is kind of what it looks like. We said the word 70, we said the number 74. 74 is the atomic number. It means how many electrons and protons are inside of that atom or occupy this atomic space. The protons and neutrons are sitting inside of the nucleus. We have 74 electrons orbiting around the nucleus. This is why it has the atomic number 74. Okay? Any questions so far? So remember the number 74. It's going to be a magical number. Okay? Let's talk about and briefly review the construct of an atom. It's been some time, maybe, that you've discussed the construct of an atom. So, as I just mentioned, we have the nucleus. Okay? Inside of the nucleus, we have protons. Around the protons, we have a balancer. That is the neutrons. The neutrons and the protons have weight. They have a mass. They are mass. Okay? Electrons are situated outside of the nucleus, outside of the nucleus, in what we call shells, orbiting shells, orbits or shells. Every particle, every substance of this atom has weight. Okay? And it also has charge besides the neutrons. The neutrons are neutral. They have no charge. They don't attract. They don't repel. Okay? Yes, everybody understand that? Positive, the protons, positive, will attract the negatives. This is kind of the ideology that we discussed. When we apply more charge to the anode, we make it more positive to attract the negatives. The electrons stay in orbit because of this attraction. And there's more to it, I promise. There's a lot more scientific to it, but I'm giving it to you in layman's terms. Got it? For right now. Okay, so because the electrons are never going to go out of their orbits unless they are caused to, they stay in their orbital shell by what we call a binding energy. Binding energy. So when I say the words binding energy, we're talking about the electrons being bound to their shell that's orbiting around the nucleus. Binding energy. Questions about the construct of an atom? Now is the time.
Miss Lara, can you repeat that again? Binding energy with the electrons that is being bound to the shell?
The binding energy is the force or energy that holds this electron to continue to orbit. One thing that you need to understand is that the electrons are not stationary. They are constantly spinning. Electrons are constantly spinning around the nucleus. And so, not to have the electrons fly off, they are bound to this path, the shell, the orbit, with a binding energy. So, one thing also, electrons are constantly spinning around the nucleus. Binding energy holds the electron to its shell. Okay, any questions before we move forward? So where do we find these atoms, Ruth? Where do we find these tungsten atoms that we're talking about? Where will we find tungsten atoms?
We will find them in the shell.
In the shell? Got to think about the words. A shell.
Tungsten.
A shell. Okay, so this whole atom. Okay, it's like saying, Ruth, show me your arm.
My atom?
Arm. Show me your arm. Okay, good. That's your left arm, right?
Yes.
Okay, is that left arm part of Ruth?
Yes.
Good. I'm not going to tell you to show me your feet, but you know where I'm going with this, right? All of these electrons are like the parts of the entire atom. All of this is one big atom. Okay? Here we have the nucleus, which houses the protons and the
Neutron.
good. We have shells or orbits outside of the nucleus that has a place for the
Electron.
good. Where can we find tungsten atoms? Pamela, help her out. Where can we find tungsten at? We've talked about it. We just reviewed it. Pamela? Yeah, there you go.
It's where you explain the binding energies where the electrons they are bound in there.
So on the focal track or the target, that's where we're going to find tungsten atoms, right? Good. And where else are we going to find tungsten atoms?
At the orbital shell.
Okay.
Atom.
This whole thing is an atom.
Filament.
Okay. And the filament, thank you. In the filament, we have these atoms in the filament, and we have these atoms in the target. The orbital shells are the rings around the nucleus. They belong to the atom. They belong there. The electrons flow in these orbital shells. They spin around. And so what is holding them in place, Isaias? What is holding the electrons in place around the orbital shells?
Maybe attraction?
What is this right here that I just talked about?
Binding energy?
Binding energy. Binding energy. And look at the word. It says energy. Energy. It's energy. And it's a type of energy that is binding the electrons to the shell. Okay? Questions? We're going to talk about how many orbits, how many shells. We already said we had 74 electrons, didn't we? So we can surmise, since it's a stable atom, it has 74 protons and 74 neutrons, right? So we're going to now label shells. And they are identified, so we're going to name, starting from the inside, close to the nucleus, going outward. Okay? And we're using the alphabet letters, but we're going to start with the letter K. The more electrons you have, the more shells you have. The more electrons you have, the more shells you have. And a tungsten atom, there are how many shells? K, L, M, N, O, P. That is 6 shells, 6 rings around the nucleus, 6 orbits around the nucleus. We start off with the one that is closest to the nucleus, and that is K. The next one is L. Here we have M, N, O, and P. Good. So we understand orbits or shells are basically the rings that the electrons are sitting in. How are they stuck there again? Through binding energy. Binding energy. So what else can we learn from this picture? Every shell, and this is the laws in physics, every shell can only occupy so many electrons. This is why we're not squeezing 74 electrons in their innermost shell. There is a balance. We don't need to know why right now. Don't. What I do need you to know is that we have the K shell, L shell, M shell, N, and O, and P shells. Okay? That is 6 shells orbiting around the nucleus of the tungsten atom. I want you to also pay attention to these words right here. Binding energy. Binding energy. What does binding energy mean again? Anyone?
Electrons bound to the shell.
Electrons that are bound to that shell. That keeps them from flying off. Go ahead.
Miss Lara, I don't understand when you say there are 6 electrons on K and L.
I said 6 shells. Look at the word, Ruth. What does shell mean? What does a shell mean? If I said define a shell, what does that mean?
It's an orbit.
Okay. Okay, so what is an orbit?
It's where the electrons.
So it's a ring,
Right?
right? If you were to put 6 rings on your finger, would you have 6 rings on your finger?
Maybe.
Yep, you could put 6 rings on a finger. You would have 6 rings, right? And if we place electrons on every ring, right, you would have electrons on that ring. It's the same thing. These are rings that are traveling around the nucleus.
So for
They
K
are
shell.
called shells.
So for K, you only have 2 electrons on
Correct.
that.
They can only have, the inner shell can only, K shell can only have 2 electrons. And the outer shell can only have 2 electrons. That is the laws of physics that I do not want to get into right now. I don't need you to know why. I just need you to know that there is a K, L, M, N, O, P. That's how many shells the tungsten has. The tungsten atom has. Okay? No? Yes, Ruth? What?
I have a question.
Sure.
The other atom, they have the other cell too, or just the same 6 cell?
No. Every atom is going to have, whether they have 6 shells or whether they have 5 shells, it depends on how many electrons they have. If they have more than maybe that's a good place to start.
Do we need to remember the name of the shells like K,
Yes,
M, P?
you do. You do have to remember the names of the shells.
Oh, okay. Thank you.
Mm-hmm. Here we have oxygen. Yeah. Here we have oxygen. This is an oxygen atom. Okay? So here we have hydrogen. It's got the number 1. One electron to 1 proton. Let's look at copper. How many shells does copper have? 1, 2, 3. Okay? So not all atoms are made the same. It depends on what their atomic number is. One, two, three, 4 for iron. So when we're looking at an atom, we're looking at the electrons that are spinning around the nucleus. And what's holding these electrons in place is going to be the binding energy. Make sense? Okay. So we're going to have to move on. So what I do need you to remember is that the tungsten atom, why are we choosing the tungsten atom? Because it has a high atomic number and a high melting point. In the tungsten atom construct, we have 6 shells, K, L, M, N, O, P. K is the innermost shell, and P is the outermost shell. I also want you to pay attention to the difference between K and P binding energy. The binding energy, meaning the electrons being attracted to the nucleus, is higher than the electrons that are in the P orbit. The binding energy, the strength of holding on to that shell is so strong in the K when compared to the P. So the binding energy of the K shell is 69, which is even a more important number. 74 electrons are arranged in 6 shells. 74 electrons are arranged in 6 shells, K, L, M, N, O, P. However, the binding energy is not the same for every electron. The binding energy as we get closer to the nucleus is stronger. It's higher. Make sense? Because the electrons that are going out.
I'm curious how we're gonna calculate how we get the 69, the binding energy for tungsten.
It's already defined for us. We don't have to calculate it. It's already defined for us. It's telling us. Okay? So, when I say how many shells does a tungsten atom have, your answer is 6. Can you name the shells?
K.
Good.
L.
Which one of the shells has the highest binding energy?
Should be K, right?
K. Good. So we've learned it. Perfect. Love it. Awesome.
Do we just have one?
Uh-huh.
I would say we just don't worry about what the p shell binding energy is. It's not relevant at all.
Not relevant. Not relevant at all.
Okay.
Good. All right. So we know that 99% of creation or the conversion of the kinetic energy from the filament electron is going to be heat. But let's figure out, or let's learn why it's only heat. So as the filament electrons enter, remember, how deep do they go, Jonan? How much do the filament electrons enter the anode target?
0.5 millimeters.
Thank you. Perfect. So as the filament electron enters the anode target, most of the filament electrons will interact with the outer shell. Stephanie, what does that mean? Outer shell electrons. What letters am I looking for?
KLM.
Not K, because it says outer shell.
Oh, the P.
P. Definitely P, M, N, those shells, right? So as the filament electrons enters the anode target, most of the interactions happens on the outer shell electrons. These incoming filament electrons do not transfer, they're transferring enough of their kinetic energy, because we know filament electrons possess kinetic energy. They are on the move. Kwani, what does ionize mean again? This is where I'm going to test y'all on your key terms. What does ionize?
Something about the electrons coming.
Yeah, something about it. Who's got it? What does ionize mean?
The removal of an electrons.
The removal of an electron. We know where the electrons are, aren't they? On a target atom. They're in the orbits. They're in the shells, aren't they? When we say the removal of an electron, we're talking about removing these electrons. Make sense? Yes, perfect. So as the filament electrons enter the anode target, most of them interact with the outer shells, but the kinetic energy possessed by the filament electrons are not enough to cause ionizing. They're not removing the electrons from tungsten, but something is happening. They are converting or transferring their energy to excitation. So right here, where we're looking at excitation, what does that mean? What does excitation mean? Go ahead, Amy.
I mean, the only word that comes to mind is that they're excited, like they're...
Yes! What happens when you hear music? Your body starts to move, right? Or when you have to run, you are at a heightened state. Excitation is where you start to see a vibration happen. So these outer shell electrons are excited when these incoming filament electrons interact with them. Make sense? And their excitation is a vibration. They're creating that vibration. And as things start to vibrate, they're given off as heat energy. So there is a transfer of energy. We went from a kinetic energy, that's the filament electron, has now interacted with the outer shell electrons, caused excitation of the outer shell electrons, and the energy of this excitation is given off as heat. That vibration is heat. And then to give off that energy, because remember, electrons are doing what electrons do. They're orbiting around their nucleus. So they cannot possess that excited state. They cannot stay in that excited state or that vibrating state. So to get back to what is a ground or normal state, heat emerges in the form of energy. Questions? Let's talk about, make sure we understand what is kinetic energy. When we look at this image right here, we're seeing this person. Why are they moving, Aurora? Why is this person moving in this direction? What is happening that's causing this person to move?
Kinetic energy. He's going down a hill, and as he goes, it's moving faster.
Good. And so he's on a vehicle, right? He's on a vehicle, which is a skateboard, that allows for easier movement as opposed to him standing on there, correct? So he's on a vehicle, which is our tube current and our X-ray tube. Tube current is our vehicle, right? The electrons will flow over. Because the gravitational pull is pulling him or attracting him this way, this is the direction of movement. He has now possession of kinetic energy. He is moving. Where he collides, no one knows, right? However, let's take a look at this image. Doing. This gentleman is about to hit this ball that has now entered his space. Right? Now then afterwards, we see the change of this bat and the change of direction of the ball. Right? So we know that here there was some type of collision. Correct? My question to you, Duan, is what depends on how fast this ball goes in the opposite direction?
You sound like how fast the ball is going to go? Yeah.
So if I wanted to hit this ball in front of me, maybe 6 feet, would I have to put a lot of force here in my swing?
Yes.
For
Yes.
6
Like
feet?
you have to put a lot of force so the ball can go as fast as he wants.
Okay, well, let me ask you this question. Okay, so I have to apply a lot of force to go 6 feet, but what if I wanted it to go 12 feet? Then do I have to apply more force?
Yes, of course.
Good. So what I'm trying to tell you is when we're taking into consideration kinetic energy, thank you, Duan, when we're taking into consider kinetic energy, filament electrons, how fast it's moving, and how much the collide, how forceful was that collision, will determine one of two things. If the transfer of kinetic energy was not enough, not strong enough to remove an electron from the same atom that the incident occurred, where the filament electron incidentally collided with the outer shell electrons, and the transfer did not ionize, wasn't strong enough, the incoming velocity of the filament electron was not enough, heat is going to emerge. So there is a transfer of energy. So let's recap it. Electricity came into the filament got heated, created, so the electricity, electric current energy was transferred into heat energy, correct? Then the heat energy was now converted to kinetic energy, correct? Now the filament electrons collide. Now the transfer of energy, because they could not ionize, is back to thermal energy. Does everyone see that? Yes? Perfect. I can move on now? Good. So let's recap. We're talking about energy conversion. Kinetic energy from the filament electrons in the tube current, right? Because that's what the filament electrons possess. They possess kinetic energy. So the colliding of the filament electrons with the target atom does not produce ionization. If it does not produce ionization, it will cause excitation, a vibration. And what is the resulting energy? Heat. And that's what happens here. This image is showing you we have an electron with a negative charge. What is that of representing? It has a negative charge.
Electrons.
An electron. Thank you, Jaleisha. An electron. So the incoming filament electron has an incident. Close enough, well, it should be an outer shell, but close enough to an electron that it's causing a vibration. Or in order for that electron to get back to its normal state of just sitting there and binding, it's got to give off heat. So excitation will lead to heat. When we get to ionization, it's a different process. So after this, we'll start talking about energy conversion of ionization. So let me recap here. Heat and the creation or the conversion of heat, which is 99% of what is created or converted or transferred from kinetic energy into in the X-ray tube. There are 1,000 of interactions occurring in the anode target during a single exposure. So when you guys go to clinic tomorrow and you're making that exposure, just know that there are 1,000 interactions, thousands. And 99% are causing recurrent excitation and then eventually the subsequent emission of heat or infrared energy from those excited atoms. Okay? Any questions about how heat is created inside of the X-ray tube? Nobody? I've explained it so good. I love it. I'm ready to move on to ionization. Some of your facial expressions are not encouraging me to move on.
Ms. Laura, can you explain the previous slide again?
This slide?
Yes.
Okay. What specifically about the slide? What is it that you're finding difficult to understand or challenging?
The arrow, well, you said we haven't gotten to the ionization yet, right?
Yeah. Right.
Okay.
So here we have, if I were to be able to draw on this, we know that this is the direction since our incident electron is coming over here, right? Mm-hmm. We know that our cathode is over here, mm-hmm. right? We know that the electrons are coming over from the filament, the focusing cup, and going to interact in the anode. So this atom is sitting in our target. So as the electron from the tube current is approaching this atom in the base of the target, it does not transfer any of its moving energy or kinetic energy to any of the other electrons. It's merely exciting them. It's not ionizing, it's causing them to get excited. An electron passed by that possess a lot of high energy, and it's causing those electrons to get excited. So to get back to a normal, settled down state, they have to give off that excess energy that was excited before, that made them excited, as heat or infrared or thermal energy. That makes sense?
Yes, thank you.
Good. Any other questions? So, how much heat is generated in the X-ray tube?
99%.
Of how many interactions?
100.
Thousands.
How many shells does a tungsten atom have?
6.
What are the names of those shells, son?
K, L, M, O, P.
Good. What is the binding energy, Shibu, of K shell? Shibu there?
Binding energy is the energy which holds the electron to the shell.
Right, so how much is that? And we're going to talk about the unit of measure here in a little while.
So
69. 69, thank you. 69, perfect. So we are well aware of what is happening here. So that's one interaction. But that's not giving us X-rays. We have yet to discover how X-rays are still being made, right? We know how heat is generated, but we don't know how X-rays are going to be generated. Here, let's talk about ionization. Ionization, like Wani just told us, is the removal of an electron from its orbit. It's the removal of the electron from its orbit. So the kinetic energy of the filament electron is traveling across the tube in tube current. There is a collision of the filament electron that causes an electron from the target atom to be removed. Causes an electron from the target atom, the target tungsten atom, to be removed. Only when that electron is removed, the process of ionization has occurred, X-rays will emerge.
Can you repeat that one more time?
Repeat what?
Like,
it's not difficult for me to repeat what I say. So I can only go back because it goes, it's like I'm in my mojo and then it kind of leaves. And so when you guys say, can you repeat what you just said? It's almost virtually impossible for me to do that. I will never usually say it identical because I don't remember how I said it, but I know what I tried to say. The collision of the filament electron, right, that possess kinetic energy, that will collide with a target atom, causing the removal of an orbital atom, an X-ray will emerge.
Miss Laura, I just want to see if I got it. So, an electron from the outer shell of the filament interacts with an electron of the outer shell of the tungsten?
You're putting too many outer shells.
Okay.
So what is a filament electron?
It's the electrons that are boiled off of through
So
the.
it has no shell. It's an electron that's liberated. It's freed from a shell. It was once on a shell in the tungsten filament, but it no longer has a shell. It's been liberated. It has been freed of its binding energy. Make sense? So now this is a particle traveling in a group of other electrons. This one electron will interact with an entire atom, tungsten atom, that is sitting inside of the target. If the incoming electron interacts with the target atom electron, and it has the ability to remove one of its electrons, then the process of ionization just happened. Because that's the definition of ionization, the removal of an electron. Which electrons are we talking about? These electrons. Right? So, here we go. So, when you remove an electron, X-ray is produced. So read it. So give it back to me, but don't give me filament electron shell. It does not have a shell.
Okay, so it doesn't have a shell because they've already been released.
Woohoo! There you go. Yes, it's already been liberated, released. They've been removed by boiling off, by thermionic emission.
Okay, I get it. Thank you.
Good. No. Tell me what happens in your own words.
Oh, okay. So then the liberated electrons travel to the target and they end with the outer shell electrons of the tungsten in the anode target.
Any. It doesn't. Outer was when we were talking about exciting.
Okay, so
here specifically, we're going to talk about removing an inner shell electron. But for right now, how is X-rays produced? Is when you have a collision of a filament electron colliding with an tungsten atom that sits inside of the target.
Okay.
The filament, it's almost like a marble. The marble comes in and knocks out another marble. What just happened? That is called ionization. Okay? When you rip an electron away from its orbital shell through kinetic energy, a bundle of energy will emerge. That bundle of energy is called X-ray and photon, either or. Got it?
Okay.
Perfect.
Thank you.
Woo-hoo. Awesome. Anybody else? So let's talk about this. So here comes that incident electron, the filament electron. It's traveling over from the cathode side. It's coming in. It's getting close to a tungsten atom inside of the target. It collides with an electron from an orbiting shell, causing the electron that was once orbiting away. This electron now possesses kinetic energy, and this electron is now on the move. Depending on where the electron comes from, KLMNOP, the electron that is now possessing new kinetic energy is referred to as that name. So because this, what shell is this, Maricela?
Okay.
Okay. This electron is now referred to as the K electron. It is now in possession of kinetic energy, right? So think about it. You're standing still, Justly. I'm running as fast as I can. and I push you. What are you going to do? What is going to happen? Before you fall, are you going to leave the place where you were standing? Will you be moved to another place before you fall?
Oh,
So if I run as fast as I can and you're standing still and I push you back, will you move backwards?
oh, I'm not. Okay, so you pushing me back?
If I'm running as fast as I can.
Yeah, I'm gonna go down with you.
Not down. What? Okay. Let me see. Thank you, Justin. Let me see if anybody who understands where I'm trying to go here.
We're going to be knocked off before we fall.
You're going to be knocked, but which direction though, Jaleisha?
In the direction that we were pushed.
You in the direction that you were pushed. So what kind of energy do you now possess?
Kinetic?
Kinetic, because you are moving. Did I transfer some of my kinetic energy to you when I pushed you?
Yes.
Yes. So, the incoming, thank you, the incoming filament electron is going to collide with another electron, bump it out of its binding energy, send it with kinetic energy because it has just experienced a transfer in that collision of energy. So the K electron now possesses kinetic energy. The original filament electron is now going in a different direction with whatever energy it has left. Make sense? So my next question is going to be, Amy, how much kinetic energy will I need to remove a K shell electron versus a element N electron? Well, I need more kinetic energy to move this electron versus this electron.
I can't see which electron you're pointing at. The mouse is not moving.
Oh, it's not moving? Oh, can you see it now?
No.
No, it's not moving? Yeah. Okay, so let me ask you this. So looking at this image, how much energy do you need, the incident or filament electron that is coming in, will you need more energy to remove a K shell electron versus a P shell electron?
Yes.
Yes. So to remove this, because we just learned the binding energy that is measured in electron volt, EV, volt. There goes that word, because we're going to start talking about voltage. Yay! All right. So the binding energy that is holding the electrons in the K shell is much higher than the electrons in the P shell. So it will take more force to move it. Make sense?
Yes.
Because it has a higher binding energy. Do I have any questions about that? We all understand what ionization is. We all understand that the incident electron is the one that is actually colliding or interacting with the target atoms. These incident electrons are called filament electrons because that's where they originated, from the filament. Make sense? Good. So we're going to talk about the two types of X-rays that can be produced. But go ahead and take a break, and we're going to review these words when you get back. So go ahead and take a 5-minute, go to the restroom, do what you need to do. But I'd like to review these words. Amy, do you have a test? When is our test on this? I don't think I printed out my new syllabus yet.
On the test is, for this class, it's going to be next Friday.
Okay. Thank you. Okay, good. Needed that because we still got a ways to go. All right. Okay, so let's talk about these terms. What is the difference between an electron and a photon? But I want you to give me specific in the terms of how they are completely different in description. Who wants to tell me what's the difference between an electron and a photon? Because they are not the same. Go ahead, Jonan.
An electron is a negatively charged particle, and a photon
That belongs to what? That belongs to what?
It belongs to an atom.
To an atom. And what is a photon?
A photon is a bundle of energy.
Bundle of energy. That does it have a charge?
No.
Does it have mass?
No.
It can go through walls.
Mm-hmm.
It can go through a person. An electron cannot. Correct?
Yeah.
Does everyone understand that? That is so, thank you, Jonan. Beautiful. Let's see, Jolie. Where is a filament electron? What is that? A filament electron. Why does it have it? Why does this electron have a name? A filament electron.
The filament is in the tube turn.
It's in the cathode. So that's where
Yeah.
the electron filament electron came from where? The cathode, correct?
Yes.
Good. So it is got a name. It's got a name. It tells you where it comes from. Perfect. What is a target atom, Luke?
It's the point on the focal track that it hits.
So it's an abundance. The focal spot, or the actual focal spot, has an abundance of what type of target atoms. What kind of atoms are they? What's their atomic number?
The tungsten
74.
atoms?
74. Good.
Yeah,
Tungsten atoms. Thank you. Sharon, what is tube current?
It's the flowing of the electron
From what to what?
from cathode to anode.
Perfect. Great. Let's see. Moving on. Naomi, what is kinetic energy?
Kinetic energy is energy that's moving. In motion.
Moving energy. So if you are in motion, you are in position of kinetic energy. Perfect. Love it. Ionization, Ruth, what is that?
It's the move of the atom.
From where? The removal of the atom?
Yeah.
Think about your words.
Oh.
It's not the
It's the-
removal
it's
of an atom.
The removal of the electron from the atom.
Perfect. That's correct. Good. Excitation, Maricela. What does that mean?
When an electron gets excited.
What kind of energy do they give off to get back to normal state?
Kinetic energy? No, heat. Sorry, heat.
Heat. Good. When you guys go dancing, who loves to dance? Right? The music is exciting you. Do you get sweaty after a while? Yes? No? Nobody dances? Pamela, you raised your hand. You get sweaty after dancing a long period of time?
Yes.
Right. And sweat is a type of what kind of energy? Thermal. Heat. Right? You get hot. So you got to go sit down somewhere and get cooled off. Tracy, what is binding energy?
Energy that is together.
Together or holding something together? Good. So it's holding. It's holding something to its place. Chiba, where do we find binding energy?
Binding energy.
Where do we find it?
That is for
What?
each shelf has different binding energy.
So where do we find it exactly on the atom? Where do we find binding energy on the atoms? I don't know. Okay. Stephanie, help them out. Where do we find binding energy?
It's the shells around the atom.
And like Tracy said, it's holding what to the shells?
It's the binding energy is electrons being bonded to the shell orbit around the nucleus.
Ooh, guys, I love it. I love it. So now we're moving into what kinds of X-rays are going to emerge from these interactions. We have two different types of photons or X-rays that will emerge from the interactions that caused ionization. And I'm putting that in quotation marks because one of the two is really not ionizing. One of the two is not really ionizing, and we're going to discuss that. So we have two target interactions. These two are in the X-ray tube. Okay, so a lot of times you'll hear these types of interactions outside of the X-ray tube, and they're not. They're inside of the tube. So we're going to start with characteristic photons. Characteristic photon is one
Miss Laura, we can't hear you. No, we can't.
Okay. Can you guys hear me now?
Yes, we can.
Perfect. All right. So when you're looking at characteristic photons, this is one of two types of photons that can emerge from the incoming filament electron. With that, characteristic interactions to create the characteristic photon is going to take the filament electron and orbital electron of the target atom. So the filament electron, which we know we already needed, right? And an orbital electron of the target atom. Same thing. But here, when the filament electron enters a target atom, right? We know that the filament electron is going to enter a target atom. It is going to strike one of those orbital electrons of the target atom. So the filament electron is going to strike an orbital electron from the target atom. Here it is. If the energy is greater, meaning if the kinetic energy of the filament electron is greater than the binding energy of the orbital electron, the electron is removed from orbit. I'll say it again. If the filament electron has a greater kinetic energy when it strikes that orbital electron than its binding energy, then the electron is removed from its orbit. Make sense? Does everyone understand what I'm saying? Yes? No? Possibly? Thumbs up? Everyone understand it? Okay, good. All right, great. So, when we're talking about characteristic interactions, this is going to be the characteristic photons. Characteristic photons. We're going to name those photons characteristic. Can only happen, can really only happen when an inner, because remember the binding energy of this shell? Can y'all see, is my mouse moving for you? Okay. Remember the binding energy of the K shell? It was 69, right? It has a lot of binding energy, stronger than any one of the other electrons. If the electron, the filament electron, comes in and strikes this electron and removes it from orbit, something has to rectify itself. This atom cannot be without 2 electrons in the K shell. It cannot continue to exist. It becomes unstable and it must rectify itself. The next orbit, which is the L shell, will release one of its electrons to fill in the K shell void. I'll say that again. If the inner shell, K shell electron, is removed from the filament electron when it collides, the L shell will release its energy for the electron that is closest to that void, so that the electron, the L shell electron, can now sit in the K orbit. Okay? Yes? Everybody understand what I'm saying? But it continues, because how many shells do we have inside of a tungsten atom? 6. Well, now there's a void in the L shell. So what's going to happen next? The M shell is going to release one of its electrons that's closest to the L shell void and drop down. It's going to drop down and fill in that void. So with that being said, this is called a cascading effect. A cascading effect where every electron is going to release its binding energy to fill in the next shell that was missing, that lost their shell, which was the K shell. So let's put it all together. And characteristic interactions is when an incident electron knocks out an inner shell electron from its orbit, and the outer shell electrons drop to fill the inner shell vacancies. When they do that, they have to release the binding energy that it possessed while it was sitting in orbit. The binding energy that is released will emerge as a bundle of energy called the X-ray or photon. I'm going to let this soak in. I'm going to let you bathe in these words.
Miss Laura, this is a part where it always gets me when it comes to atoms. So after the cascade process happens, in the last shell, well, one of the electrons has to go into the next shell, right?
Right.
So where does that other electron come from to fill the outer?
It'll stay empty.
Okay.
It'll stay empty. So at the P shell, it will stay empty. Okay? So now what kind of charge does this atom possess?
Would it be positive?
It will, because it's lost one of its balancing electrons. It will become positive. It's now in search of a stray electron to make it balanced again, right? It's now in search of another electron. And so a lot of these filament electrons will eventually settle in to make these atoms whole again. Questions?
I'm just wondering, K shell, L shell. So K shell, the maximum can hold only 2. It's already stable. So how are we gonna make interaction with other atom? Okay, the last one can hold only 1. Am I right?
The last one?
The last shell, like a P shell.
Can only hold 2.
2. Okay. So how are we gonna make if the electron, the K shell, if it can hold only 2, we already stable, so we cannot hold more electrons. So how are we gonna make it?
You're right, not in K shell size. So that's what's happening. So the K shell, if you look at this picture, the incident or filament electron came in, knocked out a K shell electron. The K electron is now possession of what? What kind of energy is this electron in now possession of?
Positive.
What kind of energy does this electron possess now? Because it is now in motion.
The kinetic.
Kinetic. So when this electron was released, its bond was broken. Its bond was broken. That bond energy or that binding energy emerged as a form of bundle of energy. That bundle of energy is now called a photon or X-ray. So since we have a void here, we now need to fill it. So the L electron will release naturally. It's going to release its energy so that it can move to the K shell. So another photon emerges. Well, we got to now fill in the void for the M. And it keeps going until we get to P. But my next question is going to be, which ones of these photons are going to be higher? Are going to have a higher energy? The K. Why? Because the binding energy for K was at 69 keV. Correct? It starts to dramatically go lower as we get to the P and N shell. Okay? So some photons from this type of interaction are going to be stronger than some of the others. I know, this is a lot, but taking it super slow so that we can make sure we get to the other side of this chapter. So in characteristic interaction, characteristic is basically because outer shell electrons are dropping in to fill the inner shell vacancy. How did an inner shell vacancy happen? Because the filament electron that came in knocked it out. It ionized it. It ionized it. It removed it from its orbit. So the energy of the kinetic energy that the filament electron possessed had to be greater in order for it to knock it out. If the filament electron knocked this one out, probably not that great as over here, correct? Make sense? So, keep going. So we're talking about the characteristic cascade, the process of the outer shell electrons filling the inner shell vacancies. That's what the characteristic cascade is talking about. You drop down to fill in a vacancy for the inner shell. Any outer shell electron may fill an inner shell vacancy, but it is most likely going to be proximity. Any questions? We'll stop here. So let me go ahead and review for any questions. I need y'all to read your book. I need you to read your book all the way through characteristics, because once we get through Bremsstrahlung, we're going to go into tube filtration, which is a whole nother entity in itself.
Ms. Laura,
Go ahead.
Does the so if the filament electron strikes the K shell electron, does that K shell electron, does it have the same the energy that it's leaving with now? Is it the same as the binding energy?
It's minus. It's going to be, and you have some math in your book. It's going to be minus. So the kinetic energy that was possessed, right, coming in, the velocity of that kinetic energy, and that holding of that binding energy. So when it gets moved out, it has all, if it's a K shell, it's already taken 69 keV of this energy. So now it's only going to possess the kinetic energy. That K electron is now going to possess the resulting of that separation. Does that make sense?
Okay, so they would so say for instance,
I don't want to go too much into that right now because there's not going to be that math.
Okay.
That's going to be later in physics.
Okay.
Yeah. Oh, I'm overwhelming you with new language right now, so I don't want to get into too much math until we get to inverse square law. All right, come on, questions. I know you got them. Some of you are saying, I'm just going to go back and reread to see if it makes sense. So I do encourage you to reread so that it can make sense to you. Okay? I need you to read it.
I have a question about heat production.
Okay.
So heat, the maximum has to be, say, 99, eh?
That's how much is produced inside of the X-ray tube with all of with an exposure interaction. So once you expose,
Is that like approximate number, or there has to be, the maximum has to be 99?
No, it's about a 99% conversion.
Okay. Yeah, I've seen on the console, like fluoro. Mostly,
no,
I've seen
that's something totally different. That's not heat. That's not heat. We're talking about how many filament electrons interact with the anode and create heat by excitation. We're not talking about what's on the console.
Okay.
That's coming up next. All right. So I am counting on you. I am counting on you to read. Okay? If you want to be successful in this course, it cannot be solely my responsibility to deliver. Make sense? You have to do your part to go back and read and ask the questions that you need clarification on. Do not wait for me to deliver it, because if I keep going at this pace, I will not finish with this chapter. Zoom on Monday. I don't have a problem coming here or staying here afterwards. If anyone wants to come, I just have to see how many. And we can go over some things live so that we can get some clarity. But this is important that you understand what happens here. But more important, what happened in chapter 5. Because this is building on chapter 5, if you haven't noticed already. Yes? Yeah, noticed it, right? Yeah, they did. Okay, good. Filament electrons, liberation. All right, guys, if you have no other questions, I have tortured you enough today with PRE. You have a good one.